Hello again, Physics 1015 tutorial 9 question 7. Alright, so here we look at this system. We have mercury being poured into a U-tube. The left arm of the tube has cross-sectional area of 10 square centimeters, and the right arm has cross-sectional area of 5 square centimeters. Okay, so this is a U-tube shaped. Okay. Yes, so we are pouring mercury into this U-tube, but the U-tube has got openings that have got different surface areas. Okay, as you can see in the diagram, the opening on the left is quite bigger than the one on the right, so the surface areas are different. So now on the right hand of this U-tube, we are going to pour some length of water, okay, in the right arm of the tube. So we want to determine the length of this water. Okay, we are pouring 100 grams of the water, and now we want to determine the length of the water column in the right arm of the U-tube. Okay, after that we are going to find now the distance, also, or rather the length of the mercury in the other column, which is on the left, okay, given the density of mercury. So here let us first determine the length of the water column after pouring in 100 grams of water into the right column. Okay, so the first thing to take note of are the surface areas, where they are given in terms of centimeters. We're gonna need to take those back to square meters, okay, as standard units. So we're given the mass of water as 0.1 kilograms converted to kgs. Okay, remember always to convert the units to their standard. So we are given 100 grams, and if we convert to kgs, we are getting 0.1 kgs. The area 2, which is the area of the right column, which is the smaller one, is given as 1 times 10 to the minus 3 square meters. The density of the water is also given as 1 times 10 to the power 3 kgs per cubic meters. Now the height h2, or the length of the water, is what we want to determine here. Also, we don't know the height of the mercury, but that can wait, because right now we are more concerned with the length of the water column, okay, the column on the right. So also the density of the mercury converted to kgs per cubic meters is given as 1360 kgs per cubic meters, and also of course the value of G that we already know. Okay, so now the expression for pressure, we already know that pressure equals force per unit area. Now I am writing P2 here because I am beginning with the right column. So if we consider the right column to be 2, as you can see, suggested by the areas there, the area for the right column is A2. So I'm going to go with that notation and say the pressure in the right column will be P2. Therefore, P2 is going to be F2 divided by A2. Now, what is F2? Okay, so in this case, the force applied, or rather the force that leads to a pressure for a particular fluid, is simply the weight of that fluid. Okay, so in this case we have 0.1 kgs of water, so the force therefore that will constitute to a given pressure will simply be the weight of this particular fluid. So because it is water, the force therefore will simply be the weight of the water divided by the area of the column. So we know that weight is mass times gravity, therefore weight is going to be mass of water, which is 0.1 multiplied by g. Therefore we have our expression for P2 as m2g over a2. So this is our equation 1. But also, because this water is poured to some length h, we also have to consider that as well as the density of the water. Okay, more like we take the gauge pressure into consideration also. So notice that the pressure in the right column can also be expressed as P2 equals the density of liquid 2 times G times the height of column 2. Okay, so if we equate equation 1 to equation 2, we'll have mg over a2 being equal to rho 2g times h2. Okay, so from this you can see now that it is easier to obtain the value of h2. Why? Because we know the mass of water, which is m2, we know g, we know the area for the right column, we also know the density of water, which is rho 2, and the g again. So we only remain with one unknown, which is the h2. So if we substitute those values into this expression, we are going to have the value on the left hand side we have 980, and on the right side we have 9800 multiplied by h2, from which we can obtain the value of h2 as 0.1 meters, which is the same as 10 centimeters. Okay, so this is the length of the water column. After pouring in your water, you will discover that the length of that column is 10 centimeters. Okay, so now that we have obtained the height, or rather the length of this water, let us come back and obtain the length of this mercury here. Okay, so now because the fluids are in equilibrium here, as you can see from the diagram, you add your water on the right column. Okay, you add your water on the right column. After adding all that water, then the system remains stable, or rather at equilibrium. So once that happens, it means that the pressure on the left is going to be equal to the pressure on the right. So to obtain the height of the mercury in the left column, we are going to use Pascal's principle, which tells us that the pressure on the left must equal the pressure on the right. Okay, so this is now part B of the question. So now if we do that and we want to find the height of column 1, the expression for pressure that we are going to use in this case is one which contains the variable for h. Okay, so if we wanted, we would have used this expression right here. Okay, but this one will not help us find the height for the first column, so we cannot go that way. Therefore, let us equate the two pressures in terms of the density, the height, and also the gravity. So P1, which is rho 1, density of fluid 1, which is mercury, multiplied by G times the height or the length of column 1 must equal the density of fluid 2, which is water, multiplied by G and multiplied by the length of column 2. Now the length of column 2 was just found to be 0.1 meters. So we substitute the values of rho 1, the density of mercury, which when converted to kgs per cubic meters gives us 1360 multiplied by G multiplied by the height or the length of the mercury, which we don't know. Okay, being equal to the density of the water multiplied by 9.8 multiplied by the length of the water column, which we just found. Okay, if we work this out, we'll have 13,328 H1 being equal to 980, from which we can obtain the value of H1 as 0.07 meters, equivalent to 7.5 centimeters. All right, so this is the length of the mercury column. Okay, so notice the steps that we have taken here. First, we have considered also the weight of the water which was being poured. Because we were given 100 grams, so the force in the water column there is simply the weight of the water that is being poured there. Okay, which is going to constitute to a pressure. Okay, a pressure which is also going to help us determine the value of the length by the expression of rho gh. Okay, after having found the length of the water column there, we now consider Pascal's principle, because the two fluids will be in equilibrium, so the pressure on one column is going to be equal to the pressure in the other column. Okay, so with that, we'll also be able to find the length of the mercury column. Right.